Welcome to Macmo Academy. Dear students, in this video, we will discuss and understand the topic characteristics of waves. So there are so many characteristics of waves that we need to define and that we need to understand and discuss in this particular topic. So our first SLO is to define the characteristics of waves. Define characteristics of waves. So first of all, what are the characteristics of waves? When we talk about the wave, so first thing that we will discuss is speed of wave. So as you know that if you want to calculate the speed, which two things you will need? For example, if you want to calculate the speed of an object, you will need the distance covered by an object, right? And how much time the object is taking to cover that distance. So same definition is for speed of wave. That wave speed is the distance traveled by a wave per unit time. Distance traveled by wave, distance traveled by wave per unit time. So we have the formula d upon t. The unit is same, meter per second. But here you need to understand one thing, that when we talk about the wave, so distance is actually this symbol. It is the distance of a wave. We call it lambda. We call it lambda. So by using this, we have v is equals to lambda upon t. But you already know with the definition of frequency and time, the relation between frequency and time, that frequency is equals to 1 upon t. So it means that in place of 1 upon t, we can put f, and we have a proper formula or equation for the speed of wave, which is v is equals to f lambda. So mostly we have this formula when we do calculation. But remember, if the word instead of wavelength, or if instead of length, if the word distance is used, so it also means the wavelength, and you can use the same formula for that as well. Now it depends on the question, that the time is given or the frequency is given, so according to that you can use it. It will not change the answer. But remember one thing, that this is also a sub SLO of this topic, characteristics of waves, and we have covered it over here, so we will not cover it later. So this is how we can derive this particular equation, where v is equals to speed of wave, f is equals to frequency, and this lambda is equals to wavelength of the wave. Although we will also define the wavelength after this particular speed of wave. So this is how we can define the speed of wave, and this is how we can derive the concept of this equation. Now our next characteristic is wavelength. So anyone knows about wavelength, or the distance covered by a wave? How will we like measure it? From which point to which point we take the distance or the length of the wave? Let's see. Alright, if you look at this graphical representation of a wave, and it is not necessary that every time the wave will look like this, but by taking this particular example we will understand some of the characteristics of wave. So first of all, wavelength. So wavelength, when we talk about the wavelength, second characteristic of the wave, so it is written wavelength. So if you talk about the wave, so is this a one complete wave? No, the one complete wave is from this point to this point over here, right? This is a complete wave. So when we talk about the wavelength, so it is the distance or the measurement between two successive points of a wave that are in the same phase. Means, let's write it first. The distance between two successive points, two successive means one after another, successive points of a wave that are in the same phase. Phase means that this particular upper part is called the upper phase and this particular lower part is called the lower phase. For example, if I am taking this point, okay, this point, if you can see over here, let's call it X point. So now I will see the successive point on the wave which will come next. Now I will see over here, so this point is over here. Now it will go down, but the phase is changed, so we cannot take it from here. Now it is the same phase as this one, but will you take this point? No, because it is on the left side. You have taken the point on the right side, so this point is actually the successive phase of this. So from this point to this point, the distance is called the wavelength. The distance is called a wavelength. So it is not necessary that every time you say crest to crest, trough to trough, compression to compression, or rarefaction to rarefaction, but this is also the wavelength. Maybe in the MCQs it could be asked to you that this particular option is given and you are thinking that this is not the correct answer, so this is the correct answer for the wavelength. But yes, mostly we take from crest to crest and trough to trough, right? So this is how we define wavelength, and we can calculate the wavelength by using the same formula. V is equals to f lambda, and you know that it is a length, so its unit is meter. SI unit is meter. So this is how we define wavelength. Now let's see some other characteristics of wave. Now the next two characteristics are crest and trough. Crest and trough. So when we talk about crust, so first of all we will see it on the figure over here. So the maximum displacement covered by an object from its equilibrium position, or you can call it the upper phase peak. This is the peak. From this point to this point, okay? So this is the crust. And from one crust to another crust, if we will measure, we call that wavelength. That's what we were discussing when we were discussing the wavelength previously. And the maximum displacement covered by the wave in the negative direction, we call this direction as positive and this direction as negative, or upper or lower. So maximum distance or the peak covered by a wave in the negative direction is called the trough. So this is trough 1 and this is the second trough. So from trough to trough we call it wavelength. So that's what we call crest and that's what we call trough. By the definition you can write maximum displacement. So the words are same, maximum displacement for both. Maximum displacement covered by a wave towards the positive side is called crest, But from where? From the equilibrium position. From equilibrium position. Equilibrium position. This position is called the equilibrium position, right? This position is called the equilibrium position. So from the equilibrium position or from a fixed position, if it will move the maximum towards the positive, we call that point crust, and towards negative, we call that point trough. So that's what means trough, and that's what means crust. Now the next property that we will discuss is wavefront. So let me rub this and then I will explain you wavefront. The next characteristic of a wave is wave front. The previous properties that we have discussed, characteristics or the properties that we have discussed are very common and very easy. This particular characteristic is also very easy. Now think about a wave of the sea wave. So how we draw the sea wave? Whenever we want to draw water or the river water or sea water, we usually make a wave like this. We call these waves. But have you ever noticed actually it is like this? For example, if we talk about the blades of the fan, so they all are separated. So blades of the fans are separated. But when they start moving together, so they make a circle. But actually there is no circular shape over there in reality. Actually they all are three different blades, but when they started moving together, we saw an imaginary line over there as a circle. So wavefront is also, we call we can call it the shape of the wave. We can call it the shape of the wave. Actually, when we talk about the sea water, so actually water particles are like this, and when we combine them, we can see a shape or a wave. So that this is called wavefront. So by the definition, and not necessarily every time it will look like this. It could be a circle as well. A wave is making a circle. A wave could be like this. You see on the Wi-Fi signal now. So they are signals or waves, and it is the shape that it is generating from a source and it is spreading. That's why we show it like this. On the I am talking about the Wi-Fi symbol. So they all are the wavefronts or the shape of the wave. A wavefront is an imaginary line. A wavefront is an imaginary line joining all the points, joining all points of a wave that are in the same phase. It shows the position of a wave at a particular instant, and it could be circular wavefront, it could be plane wavefront, it could be spherical wavefront, so it could be circular wavefront, it could be like this as well, and it could be spherical as well. So this is how we explain the wavefront. Now there are some other characteristics of the wave that we need to discuss, and they all are also very easy. The next one is compression. So when we talk about compression, it is the region of longitudinal wave compression. It is not present in the transverse wave, it is present in the longitudinal waves. Compressions, and the with parallel to it rarefactions. Rarefactions. So compressions and rarefactions are also very simple thing. For example, if you are walking on a road and there are so many people over there, so you will get compressed. You will get compressed. For example, the longitudinal waves shows like this. So you can see over here, it seems like that there are some areas where the gap is very low, or it is very tightly packed. The particles are very tightly packed. So these are compressed. So we call this particular area as compression, and we call this particular area as rarefaction. So this is also rarefaction, this is also rarefaction, this is compression, this is compression. So by the definition, a compression is a region of longitudinal wave when the particles of the medium are close together, producing high pressure and high density. So in this area, the particles are close together, and from this word you can understand by yourself when things are very close together, so they build pressure, the density is high. So in the MCQs they can ask that in compression phase the density is high or low, the pressure is high or low. So you can find the results by yourself by the words like these. So density is high, pressure is high, and obviously they are very, or they have distance between them, they are not close together. So comparatively the pressure is low, the density is low in rarefaction. So this is present in the longitudinal waves, not in the transverse wave. One thing that is very important is when we talk about wavelength of a longitudinal wave like this, so from one compression to other compression, this is a wavelength, and similarly from rarefaction to another rarefaction, this is the wavelength of the longitudinal wave. In the transverse wave we take crust to crust or trough to trough, and similarly in the longitudinal waves we take from compression to compression and rarefaction to rarefaction. Okay, so we have understood over here the characteristics of waves, and now we will see some numericals related to the formula that we have seen, V is equals to F lambda. So let's do some numericals problem. Alright students, if you look at this question, a wave travels with a speed of 300 meter per second and has frequency of 50 hertz. Find its wavelength. So how will we do it? So we need to calculate the wavelength, and the formula is V is equals to F lambda. So speed is given 300, frequency is given 50. We can easily calculate the wavelength, but in this question, instead of frequency, if the time period is given, we can find the frequency by using this relation, that inverse of 1 upon of time is equals to frequency, right? And similarly, you know that wavelength is meters, so your answer must come in meters. Right now it is given meter per second, so it is fine. But if it is not given meter per second, so first we will calculate it, and then we can convert our answer to the meters. So why we are discussing this? Because in the MCQ sometimes it will happen like this, that maybe the value is given in centimeter per second, and there is no option which is correct with respect to centimeter that you are calculating. So it means they have converted the final or the correct answer into meters. So that's why I'm discussing it, and it is very important. So lambda is equals to 300 upon 50. So your answer will be 6 meters. So the wavelength of this particular wave is 6 meters. Here I want to discuss one very important thing, that for example if you look at this particular wave, and similarly I am drawing over here one more wave which is like this. So if you will look at these two waves, the blue one has low wavelength. You must make connections like this, otherwise you will not be able to solve the paper questions. And it has more wavelength. It has less wavelength and it has more wavelength, or the wavelength is more than that one. So if I ask you about velocity, what will you think? As everything is same for these two waves, so remember about that concept of distance. If this wave is traveling more distance, it is covering more distance, the wavelength is high, So what we call that the velocity is higher of which one. So what I ask you that you need to think about it, that which wavelength has high speed or high speed, this one or this one, which one? Think about it and then reply me the answer of this question, that if the wavelength is low then the speed is high, or if the wavelength is more then the speed is high. So you need to think about it and then tell me the answer of it. Now let's see another question. Now in this question it is written a wave has a time period of 0.02 seconds. So time period is given 0.02 seconds and wavelength lambda is given 4. We need to calculate the frequency and speed. So first of all, as we know that frequency is equals to 1 upon t. So it will be 1 upon 0.02. So it will come, what will be the answer of it? 50 hertz. Now we can easily calculate the speed by multiplying frequency with lambda or wavelength. So 50 multiplied by 4. So the speed of this wave is 200 meter per second. So these are some of the examples of the numericals related to this formula, V is equals to F lambda, and for this you need to remember this relation as well. F is equals to 1 upon T, or T is equals to 1 upon F. So in this video we have understood the characteristics of waves, the derivation of this relation V is equals to F lambda, and some problems related to V is equals to F lambda and frequency and time period. Thank you for watching the video, and if you like the video don't forget to subscribe our channel.